Hello guys, in this video I'm going to go over our worksheet questions. So let's work on question number 1. Here it's asking you to write down the stepwise mechanism. The way we're going to work here is that we're going to react with sodium hydride and then we're going to react with methyl iodide. So as we see here, this is nothing but just a Williamson ether synthesis, right? So when we consider sodium hydride, we want to consider as this sodium, and we have a hydride, a negative sign on it. Right, so sodium plus and chloride hydride minus. So this hydride is very basic character, so it's going to get another hydrogen from this hydroxide. Okay, so we have cyclopentane here, and then on the cyclopentane we have a hydrogen on this oxygen, right? Oxygen is a very electronegative element, and it's going to polarize the bond between hydrogen and the hydride on sodium hydride. It's going to take the hydrogen from there, and then we're going to have the lone pair on oxygen. So once we have that, we're going to have this negative sign right here. So this alkoxide, cyclopentane alkoxide here, is going to react with this methyl iodide, right? Okay, so this alkoxide ion is a negative charge, is looking for a polarized, a positively charged carbon. So we have hydrogen here, hydrogen here, hydrogen here, and then we have iodine. This is methyl iodide. So this alkoxide is going to react to this carbon, and this iodine will leave, since carbon cannot have more than 4 bonds, right? And then we're going to get this. And then iodide will be left over with sodium, right? So this is the mechanism for reaction 1. Second question is asking, refer to exhibit 8.1, mechanistically, Williamson ether synthesis outlined above is, this is nothing just by SN2, right? So this alkoxide comes in and iodine leaves. That's called SN2. So the SN1 mechanism, if you have a tertiary carbon here, iodine will leave by itself because tertiary carbon cation will be positive, will be stable. So this is called SN1 process. E1 and E2, they are the elimination. They're not substitution. So this is the one we have here. Okay. Question number 3. So it's asking you to, alternatively, the cyclopentyl methyl ether may be synthesized from cyclopentene. So this is cyclopentene, right? Okay, outline the synthesis of cyclopentyl methyl ether from a cyclopentene. So how can you make the same molecule here, the same molecule, starting with this? Well, here, this is going to be going with the mercuration, right? Alkoxymercuration of alkene. So, in this one, we're going to react with mercuric acetate, or we can call mercuric acetate, or we can react with a trifluoroacetate, right? So I'm going to write here mercury acetate. This is fluoro, 3-fluoroacetate. And we can do it in methanol, since we want to add this alkoxy group, methoxy group to our drink, right? So once you react with this 2, we are getting mercury attached to our drink, CF3. And here we're going to get the methoxy. I can show it like MOA, but I'm going to make it clear that it's CH3, right? Let's do it this way. So now we are going to reduce this molecule into the hydrogen. So we're going to get rid of this mercury acetate. So I can react with sodium borohydrate to reduce to hydrogen here. And then we're going to get a methoxy here. Alright, this is how you can make a double bond to ether. And then this one, how can you make an alcohol to ether? In this question, we are interested in cleavage of ethers by hydrogen iodide or hydrogen bromide. We can say an acid, right? So the first process will be, we're going to protonate the hydrogen oxygen here, and then it's going to be positively charged, and then this bond, or this is the case 1, or this one, this is the case 2, is going to cleavage, and then we're going to form, there are two pathways. One is iodide or bromide will attack from the back, from here or here. The second case is that you're going to form a carbocation on this position, like in the 3 position, and then you're going to attack to the bromide or iodide. So which ones are possible here? None of them are possible. So back attack is not available. For example, once we protonate here, and then we have a positive charge, so now the iodide is going to attack from the back, right? This is not going to be possible because it's an aromatic ring. So this is not allowed to get in from this side, right? There's no room here or in this side. So this is not going to react with SN2 pathway, because the back attack is not available. So can we have like SN1, which is forming a carbocation here or there, so the iodide will attack? Well, this is not also possible because it's positive charge on a ring. It's not going to work. So there's no way. This is not stable at all. So this is not going to work either. So this reaction is not going to go through because the backside is covered, and then this is not a tertiary alcohol, a tertiary carbocation, right? The intermediate is not. Okay, so this is question number 4. Let's do question number 6. Alright, so let's go to the next question. How can I go to the next question? Here we go. Question number 6. Write the complete stepwise mechanism for the reaction below. Show all the electron flow with arrows and draws all the intermediate structures. Okay, so here we have an epoxide, right? So we have an alcohol, we have an acid here in epoxide, so we have hydrogen OH2 positive charge on it. So obviously this oxygen's electronegative is looking for a proton, so it's going to react with this hydrogen, and then we're going to get water. So once you have that, so we will have hydrogen here, methyl here, CH3 here, and then we have this oxygen, right? Okay, let me erase this part. This epoxide. Okay, so we have a positively charged epoxide here. Obviously, this is gonna be not stable, so tend to open up, right? So since this opening up is not gonna be by itself, so what's gonna happen here is that H2O water will attack from the back, and then it's gonna open up this bond here. Okay. So we'll have our ring here, cyclohexane here, and then we're going to attach the hydroxide, which is this guy, unlike the epoxide. Oxygen is going to be right here, hydroxide, and then we're going to have the methyl on the top of that, where we have OH. And also we have hydrogen here. This is going to be positive charge. So this is the one water attached. Since you cannot have a positive charge on oxygen here, the water H2O will get to this hydrogen, and then this lone pair will be on oxygen, right? And then we're going to get the product. All right. That's the CH3. That's the OH. And that's the product. Alright, so also we are going to have a hydronium right here. It's going to be hydronium. So acid here is going to be colorless. So we use the acid, and then we end up having acid. We put it back. That is question number 5. Alright, so let's continue next question. Next question is asking acetals are a special class of ethers which have 2 ethers linkage with a single carbon. So this guy right there. Okay. Alright, it's asking us to find out. Refer to exhibit, draw arrows showing electron flow for this reaction on the structure provided below. So we have provided the reaction mechanism, which is good. So now we're going to just follow, we're going to show where the arrows are going. As we know, arrows are going to be shown as electrons, right? So we are moving electrons. So for the first case, we are going to move this lone pair to this hydrogen, and then this is going to go to the water. So now we protonate the oxygen here, ether, so we have a positive charge on it. So this is not going to be stable, right? Because this is going to move here to make this positive charged ion right here is going to be positive here. So why this is preferred? Because there's a stability provided by this oxygen, so you can make a double bond right there. Right, this is the resonance structure. So we have a resonance structure here with this oxygen. So it's stabilized. Okay, so now this is stabilized positively charged will be attacked by the water. So we can move this water here, oxygen here, the lump here, and then so this now we have the positive charge on it. So this hydrogen will move, right? Will go away by another water. So I'm just showing you more steps here to see where they are going. Okay, this is how it's done. Question number 7. It's asking you, this ether cleavage occurs so easily under such mild conditions because the carbocation intermediate in 2 steps is very stable. Explain why this carbocation is stabilized. As we explained here, because of this resonance structure, right? That's the resonance structures we can get, so this is stabilized because of this. Alright, so let's go to the next question. Next question is asking when 1,2-epoxy propane is treated with sodium ethoxide in ethanol, 1-ethoxy 2-propanol is major product, while only trace amount of 2-ethoxy 1-propanol is produced. Explain why these results are based on the reaction mechanism here. So here we have an epoxide. Epoxides wants to react with SN2 process with alkoxide, right? So we have a negative charge oxygen here. This oxygen will relieve this strain here on this ring, so it's going to attack to open it up, right? So this lone pair here, we have a negative charge on this oxygen. This oxygen is going to attack to one of these carbon, to the right or to the left. Now the question is, which one is more feasible to do that? Obviously, less hindered one is going to be more available to be reacted. So it's going to open up here, and it's going to form from the right. So once we do that, we're going to get this major product. We have a trace amount of reactant from reacting from the other side. So once this oxygen reacts with the second pathway right here, this is also possible, but being a steric hindrance with the methyl group is not going to be preferred way to do it. So this is going to be a trace amount. Okay. All right. Question number 9 is asking you to write down the arrows. So this reaction, once we are provided the reaction mechanism, I think it's going to be easier to find out the arrows, right? So all the time, the tail of the arrow is going to show where the electrons are coming. The tip of the arrow is going to show us where the electrons are going, right? So in this case, we're going to have this double bond to react with this chlorine, and then this chlorine double bond in between the chlorine is going to go away, and then we're going to form this chlorine transition state, right? So the chlorine is going to attach to our molecule, and now water molecule is going to attack to this chlorine here to open up this ring. So you have this product right there. The thing is that once the water attacks here, is not gonna, the hydrogen will be eliminated, right? Hydrogen will be eliminated by water. That's the step 1. On the step 2, we're gonna react with a base. So this base obviously gonna get this hydrogen all the time, and then we are gonna have the negative charge on this oxygen. So once you have this oxygen and alkoxide ion, well, you have a hydrogen here, halide here. This is gonna right over here. This is like a Williamson synthesis, right? And then you're gonna have this epoxide, and this is gonna leave obviously, right? Okay. I'm gonna continue on the next video.